Hey there folks, Mr. G again with another educational video. This is part 2. We talked about special angles and special triangles in our first part. If you haven't seen that, go watch it. In this one, we're going to be talking about special angles that are bigger than 90 degrees. So first, what we're going to do is just draw some angles and see how we can relate them back to the special triangles that we saw in the last video. Let's take an example of an angle like 120 degrees. Now, we haven't been told how to calculate special angles for 120 degrees, but we still know how to make this into a triangle. The way that we did that when we were talking about sine and cosine for larger angles would be to take our terminal side here, draw a line straight down, and now we have a right triangle. Now, the angle inside here isn't going to be 120 degrees. This is actually going to be 60 degrees. And that 60 degrees comes from the fact that this whole rotation, the whole half rotation is 180. If this is 120, the rest of it needs to be 60. If this is a triangle, this is 60, this is 90, this angle would have to be 30 degrees. Now you might already be thinking to yourself, wait a minute, we did this triangle before. And you're right. If we go and scroll up a little bit, we see this exact same triangle up here with 60 degrees and 30 degrees over here. So what we could do is if we make this radius, let's say we call it length 2, we can make it any length that we want, let's say we make it 2, that would make this side root 3 and this side over here equal to 1. Except for one thing, our height is still positive, but now we're going in the negative direction because we're on the left side of the y-axis, so this length here would technically be equal to negative 1. So by going larger than 120 degrees, we can get back these same triangles, but now the signs of x and y might have changed. What if we take another example, like 225 degrees? In this case, it's going to be bigger than 90, bigger than 180, and about halfway between 180 and 270. So that's how we would draw 225 degrees. If we wanted to make this into a triangle, we would drop a line straight down here, and now we've got our right triangle. But what's this angle right here? Well, if it's 225 and this half turn is 180, it's the difference between 225 and 180, so this angle right here is 45 degrees. This angle would also need to be 45 degrees since all of these three angles need to add up to 180, but we've seen a triangle like this before. We know that 45 degrees, and 90 is the same thing as this one up here. It's just been rotated a little bit. So if we make each of our sides equal to 1 in this case, our radius here would be equal to root 2. But again, we're not going to be positive 1, it's going to be negative 1, since we are in the negative x and the negative y direction. So it's the same triangle in terms of the size of the sides, just the sign has changed. So we can get these same special triangles, same special angles, except for that our values for x and y might be positive or negative. Now remember, from last time we defined that r is always positive, but the signs of our sides could be positive or negative. What we see from both of these examples is it's not our original angle, but this angle right here, the angle between our terminal side and the x-axis, that's important. We have a special name for that angle, we call that the reference angle. So for angles that are bigger than 90 degrees, what's really important is to figure out what the reference angle is. Because that reference angle, if it's 60 or 45 or 30 or whatever it is, tells us which special triangle that we have. We can figure out the signs, whether it's positive or negative, by looking at which quadrant our angle is in. So for 120, we're in quadrant 2. For 225, we're in quadrant 3. We can use that to figure out the sign of our trig ratios. So let's do one example of that. Let's say we wanted to figure out the cosine of 120 degrees. So this is like our diagram on the left here. This is going to be equal to either plus or minus the cosine of the reference angle for 120 degrees. And this plus or minus is going to depend on our quadrant. As we can see from our diagram, our reference angle for 120 degrees, we drew it out, this is going to be 60. To figure out our plus or minus, what we need to do is go back to that diagram that we drew that tells us which quadrants have positive trig ratios. So this tells us where it's positive. So this has all of our trig ratios are positive, just sine is positive, just tan, just cos, positive. I was looking up some ways to help you remember this, and I came across one that I kind of liked, which is add sugar to coffee. So that helps us remember the A, S, T, and C in order of quadrant 1, 2, 3, and 4. Now our quadrant in this case, we're in quadrant 2. We drew our picture, we figured out we're in quadrant 2 here. That tells us that cos is negative. So we want the negative cosine here. And we can go back to our pictures that we drew last time, figure out what cosine of 60 degrees is. As we can see from our diagram here, cosine of 60 is equal to 1 over 2. So putting this all together, we get the cosine of 120 degrees would be -1/2. Now you can do this for a bunch of different angles, including negative angles. And the book actually has a really good summary of this. So if you look in the book on page 276, it has this table right here, where all that we're doing is going along all of our different angles. You could figure out the reference angle and then figure out the sine, and you could fill in this entire table here for sine, cosine, and tangent. I added little annotations here. When it says infinity, what it really means is undefined. Now you could also do this for all of the negative angles. So if we go from 0 all the way to -330 degrees, so if we go backwards around our circle, we actually get the same values, but the signs have changed a little bit. I would encourage you, if you have the time, to try and reproduce some of these tables here. In particular, the negative table is a really great exercise. We can also summarize these two tables really neatly using a graph. And to do that, I'm going to go to Desmos. So this is our first graph here for sine of an angle. So as we can see, sine of 0 degrees starts off as 0, which if we go back to our table, we would see. Once we go to 30 degrees, we get our first special angle where sine is equal to 1/2, like we saw in our calculations. When we go to 45 degrees, it comes out to 0.707, which if you calculate out √2/2, will match to 3 decimal places. If we go to 60 degrees, we get 0.866, which if you did √3/2, you would also get match. And then finally at 90 degrees, we go up to 1. And this continues as we go along our graph here. Now we see a similar thing when we add the cosine graph here. Except for in this case, we now start with 1. We go down. At 30 degrees, we get our √2/2. At 45 degrees, our graphs match at 0.707, √2/2. At 60 degrees, we get 1/2. And then at 90 degrees, we go all the way down to 0. Now you might have noticed that these graphs look very similar. They almost kind of look like the exact same graph, just shifted a little bit. And you'll learn about why this is the case next year when you do more trigonometry. But if I take my graph and I shift my angle by 90 degrees, I can get cosine and sine to look like the same graph. Now the last one I want to show you is tangent, which looks a little bit like this. We start off with 0. At 30 degrees, we get 0.577, which is 1/√3. 45 degrees, we get 1. At 60 degrees, we get 1.732, the same as √3. And then as we get closer and closer to 90 degrees, this is where we shoot off to infinity because we're dividing by 0. If you remember, this is where it's undefined, so it keeps going up and up and up. It's never going to get exactly at 90 degrees because it's undefined there. And then it continues this pattern as it goes along. As you can see, this looks very different from our sine and cosine graphs that we saw before. But importantly, all of these graphs here have a sort of repetitive or periodic characteristic where they keep repeating over and over again because as we go around and around our circle, we're going to see the same patterns every single time. You'll learn more about this in Pre-Calculus 12. That's the end of our second video. In the third video, we're going to be going over a little bit about how to solve the kinds of problems you're going to see in your workbook. See you then.